Yep. OK. So we're now live. Thanks, everyone. Thanks again for the in-person audience and the virtual assistants. Yeah, just a reminder for the virtual ones, if you want to interact with us, you can send emojis during the talk, and also you can add questions in there. I'll be glad to read them to our speaker today. And also we'll have some time for Q&A at the end. Also in person, I'll be moving the mic around, so if you guys have any questions. All right. So today we have a software engineer from VMware. He joined the RabbitMQ team about 3 years ago. And well, he's now here to give us an outlook on the performance improvements and the future of RabbitMQ. So, well, welcome, David Ansari.
Yo, hi. I'm David, and this talk is going to be about RabbitMQ performance improvements. So that's the agenda. We will also talk about a bit more about RabbitMQ architecture and how it's implemented in Erlang and how it leverages the Beam virtual machine. So RabbitMQ, as you know, is a message broker. It has support for multiple protocols. So the core supports AMQP 0.9.1. So AMQP stands for the Advanced Message Queuing Protocol. And RabbitMQ got first released in 2007, and the AMQP 1.0 spec was released 5 years later in 2012. So AMQP 1.0 is also supported by a plugin, and MQTT is supported by a plugin. Same applies to Stomp. And since last year, RabbitMQ also supports a new binary stream protocol. As I learned, for example, last week, RabbitMQ also supports, for example, sending emails to and from RabbitMQ. Not sure how useful that is, but it shows how easily you can extend RabbitMQ by further plugins. All right, so we start with RabbitMQ architecture. So AMQP 0.9.1 does not only specify the protocol between client and server, but it also specifies certain server objects. So for example, it defines exchanges, and queues, and bindings. And usually the client applications, they declare queues, bind it to an exchange, and then depending on those bindings and exchange types, a message is routed from the publishing application to a queue where the message is stored, maybe persisted, maybe replicated, depending on the queue type. And from there, the consumer picks it up and reads the message. Now, there can be many exchanges, many queues, many bindings. There can also be many client applications. And the challenge is here that RabbitMQ needs to scale with the number of queues, exchanges, objects being created. So some customers, for example, have hundreds of thousands of exchanges, bindings, and queues, and also thousands of client applications. Now, this is how RabbitMQ implements AMQP 0.9.1. So as you all know, Erlang OTP implements the actor model. And in RabbitMQ, connections, channels, and queues are implemented as actors. So that's represented here by these orange stick figures. So there are Erlang processes. And how it works, the publisher sends a message to RabbitMQ. Then we have a connection reader process, which knows how to decode the frame from the wire. It then sends the message to the channel. So the channel is just another AMQP concept. It's a virtual connection. So channels share the same socket. A single network connection can carry, therefore, multiple channels. And then the channel forwards the message to the queue, depending on exchanges and bindings. So exchanges and bindings, in theory, you could maybe implement them as Erlang processes as well. But I mean, the state is rather static, right? So it's cheaper to have them just an entry in Amnesia. And then on the consuming side, the message is sent from the queue to the channel, and the connection writer writes it to the consumer. Now, because connections, channels, and queues are implemented as actors, RabbitMQ as a message broker provides scalability, performance, and fault tolerance. So it provides scalability because as the number of client connections increases, new Erlang processes are cheaply spawned. It provides performance because with many CPU cores, connections, channels, and queue processes just run in parallel, so you get high message throughput. And it provides fault tolerance because, for example, if a connection process crashes, it only affects that connection process, not the ones from the other clients. And the best thing here is that RabbitMQ gets scalability, performance, and fault tolerance basically for free, just by being implemented in Erlang and running on the Beam virtual machine. Now, this sounds all nice in theory, but the question is, do we really achieve, for example, linear scalability? So often you might see that, for example, your publishers experience a high publisher confirmation latency, or that you are not getting the message throughput that you're wishing for. And in that case, we need to find the bottleneck. So is it in the network or in RabbitMQ? And if it's in RabbitMQ, in which actor is it? Often, the queue process is the bottleneck. Why is that? Because the queue process does the most heavy work. So it needs to write the messages, for example, to disk. Or if it's a replicated queue type, it needs to send the messages to other Erlang nodes. So therefore, having a single queue is an anti-pattern. And the solution here is that your client applications ideally define multiple queues. There are some plugins in RabbitMQ which can help, for example, the sharding plugin or the consistent hash exchange plugin, so they distribute the messages a bit more transparently across the different queues. Also, traditionally, there has been a single queue type, what we nowadays call the classic queue. So it's highly configurable. And that classic queue also has a mode for high availability. So that's what we today call classic mirrored queues. Classic mirrored queues come with some weaknesses. So new queue types have been developed in recent years. So most importantly, quorum queues. They, for example, replicate messages faster than classic mirrored queues. And streams, which also write messages much faster to disk than classic queues. So we will talk a bit more about those queue types in the next few slides. But just one remark here, maybe it's also okay to have not a queue at all. So that's nothing which exists today in RabbitMQ, but if you imagine, for example, for MQTT workloads, so if you have a quality of service 0, which means at most once, maybe it's good enough to just send your message to any currently online consumer. So imagine you send your message directly from the channel process, from the publishing channel process, or the publishing MQTT connection process, to the consuming channel process, or the consuming MQTT connection process. There's no need to really store the message, right? So that's something to think about. We're currently experimenting with it, and this might achieve better scalability and better throughput. But yeah, so there are classic mirrored queues, quorum queues, and streams, and now we look at them in a bit more detail. So this is how classic mirrored queues look like. So first of all, those pictures were made by Gerhard Lasu, so thanks for providing them. He presented them at last year's Systems at Scale. But basically, the publisher sends a message, as we said earlier, to the connection process. It then forwards the message to the channel process and to the queue process. And what happens then with classic mirrored queues is that we have something called a chain replication. So the message is just sent in a ring fashion from RabbitMQ1 to ARMQ2 to ARMQ3 and confirmed back to ARMQ1. So this is a 3-node RabbitMQ cluster, and the messages are sent via the Erlang distribution. Now, as you can imagine, if you have 5 nodes, for example, this becomes slow, right? Also, classic mirrored queues, they failed the Jepsen test suite. So under certain network partitions, messages could basically get lost, although the publisher already got a confirmation, which is not what you want, right? So as an additional mechanism of defense, the message is also sent from the channel process to the secondary. So if you send a single message in a 3-node RabbitMQ cluster, they end up being sent around 5 times. So they're slow and error-prone. And that's why today classic mirrored queues are deprecated. So they're going to be removed in RabbitMQ 4.0. What you should use instead are quorum queues. So quorum queues are based on the Raft consensus algorithm. And as you all know, consensus means multiple servers agree on a value. Now in Raft, that value to agree on is a log of operations. And in quorum queues, the log of operations includes, for example, a message is published, a message is consumed or a message is acknowledged. There are a few more operations. For example, a consumer subscribes to a queue or a consumer is down, so an Erlang monitor fires. So this is also written to the log. And Carl implemented a Raft implementation for Erlang and Elixir called Ra. And in this library, it supports many Raft clusters for a single Erlang cluster. So it's a bit targeted towards the RabbitMQ use case, because in RabbitMQ we want to have multiple quorum queues, right? So maybe we want to have hundreds or thousands of quorum queues. And each quorum queue is its own Raft cluster. Now, if you're curious about quorum queues, I recommend watching Carl's keynote from, I think, last month at RabbitMQ Summit in London. It's now on YouTube, so very good talk. But this is how it looks like with quorum queues. So a message is being published, and again, the message goes to the connection process, to the channel, to the queue process. And now from the queue leader, the message is sent to the queue followers. And the followers write the message to disk in the Raft write-ahead log. And once the leader got a confirmation from only a majority of nodes, that log is set to be committed. And then every Raft node or every quorum queue leader and follower apply that log to its state machine. Now, the state machine of a quorum queue, of course, contains the queue of messages that the publisher were publishing. But it also contains a bit more. So, for example, it contains yet another queue for messages that got returned by consumers. For example, if they reject the message with requeue true, or if they dead letter message, there's another internal queue in that state machine for dead letter messages to safely forward them to dead letter exchanges. And that state machine also, for example, contains a bit more configuration of how the queue is set up, of what consumers are currently online, and so forth. On the consuming side, which you see on the right in green, a consumer can basically connect to any node in that Raft or RabbitMQ cluster, and it can then consume locally from that node, so it does not need to contact the leader. So that's why quorum queues also provide much more safety, because that state machine is deterministic. Once a log is committed, we get those safety guarantees, also in the presence of network conditions. Now, also last year, streaming were added to RabbitMQ. So a stream in RabbitMQ models an append-only log. It's persistent and replicated and has non-destructive consumer semantics. So what this means is if you read a message from a stream, it's not going to be removed from the stream. So that's different with queues, right? If you read a message from a classic queue or quorum queue, that message is removed. Consumers can attach, as you see in this picture, based on an offset to the stream or based on a timestamp. And then they can do like time traveling, and you can have many consumers which consume from the same stream. So basically you achieve large fanouts. They provide very high throughput. And if you're interested more about streams, Arnaud wrote a very good series of blog posts, which you find in the link on the bottom here. But this is how sending and consuming a message looks like with streams. So the publisher sends the message via a new binary custom RabbitMQ stream protocol to the, we call it stream reader. It's a new connection type. Then the channel is being skipped because it's a stream protocol. Channel is AMQP specific, right? So the message is sent directly to the stream leader. And then the message is sent via dedicated TCP connections. So this bypasses the Erlang distribution to the stream followers. And for that, the send file system call is used. So it copies data between file descriptors within the kernel, and that's very efficient because the message data does not have to enter user space for replication. The same applies to consuming a message, again on the right side in green. So if a message is consumed, send file system call is used to send this segment of a specific file to the consumer directly, and then the final filtering will happen in the consumer. So, but then you obviously need a stream RabbitMQ library on your consuming application. The best part about streams is that you can also send messages to a stream with another protocol. So for example, with AMQP or with MQTT. So for example, you can send a message to a stream with the stream protocol at very high throughput and then consume with AMQP if you want to. So it's very compatible. We won't go much into the details of performance and what sub-entry batching is, but this is just to show the numbers you can achieve with streams. So for example, with 5 streams, you can achieve 17 million messages per second. So this is both publishing and consuming. And in this case, it corresponds to 380 megabytes per second. So this should be like enough for most use cases. Right, so earlier I said often the queue process becomes a bottleneck, but how do we know for sure? It can also be in the connection or in the channel process or somewhere else. So we need, of course, to measure. And this brings us to performance tools. Now, there are different load generation clients that we use in RabbitMQ depending on the protocol. So for AMQP 0.9.1, we use perftest, and perftest is written by the RabbitMQ team. It's written in Java. There's a similar tool for the stream protocol. It's called stream perftest. And then for testing MQTT workloads, we use EMQ-TT-Bench, which is a tool published by EMQ. So EMQX is another MQTT message broker written in Erlang. So for data collection, sometimes we use microstate accounting, which gives a high-level overview of what the Erlang VM is busy with. You probably know cprof, eprof, fprof. So those are Erlang-specific tools for recording function execution counts or time. The downside here is that if you want to get a call graph, it kind of significantly slows down the program. We often use RabbitMQ Diagnostics Observer. This just calls the Observer CLI, which underneath uses the Recon library. So you can use it in production to troubleshoot RabbitMQ. Now the tool which we use the most is perf. So perf is a Linux profiler. We use it for CPU and memory profiling, but that tool can do many, many more things. It's supported since Erlang OTP 24, and for us it was, I would say, kind of a game changer, because you can now create call graphs, and your program runs almost as fast as before. So it allows any Erlang program to efficiently and precisely detect bottlenecks in Erlang source code. And you see really on which function takes a lot of CPU time, for example, or which function allocates a lot of memory. So to profile RabbitMQ, we just start RabbitMQ with this jpperf_true Erlang argument. Then we start one of the load generation clients we had on the last slide. And then we just record a profile. So in this case, we say perf record past the PID of the beam process. So that's now the operating system process. In this case, we want a CPU sampling at 999 times per second. -G creates a call graph for kernel space and user space, and we do the whole thing for 30 seconds. Now this creates a file called perf.data, and you can analyze this with various tools. Probably the most famous one are flame graphs. So how many of you have seen or flame graphs or use it? Okay, most people said, then I don't need to explain much. But basically, the colors here do not matter. The height does not really matter much. So it just means maybe recursion or deeply nested functions. So not necessarily a problem performance-wise. So what you need to watch out for is how wide stack frame is. And because in this case, it says a lot of CPU time is spent in that function. Now let's discuss performance improvements. So we do first 2 examples of how those flame graphs helped us improve RabbitMQ performance. And thereafter we discuss a bit more general performance improvements across the different queue types. So the first example is the one which we just saw. So in this case, for example, we used perftest have a single producer, no consumer, and we publish messages as fast as we can to a stream via the AMQP 0.9.1 protocol, because that's what perf_test uses. Under the hood, perf_test creates a direct exchange, it creates a stream, and it binds that stream to the direct exchange. And still we see that for a function called RabbitExchange_root, it takes 9.5% of CPU time, which is quite a lot, because if you do routing, but you only have a single root, a single binding, this sounds too much. So if we zoom into that function, then we see, for example, ETS select takes a lot of CPU time, and also this one here, DB match compile, so database match compile. And if you look into how routing works, so the channel process needs to know where it sends the message to which queue. And as input, it provides the source exchange and the routing key. And in RabbitMQ, we had one amnesia table called RabbitRoot, so that's a set. And it stores the whole binding as key of that table. So it used an ETS select and a match specification in order to get out this destination queue by providing source exchange and routing key, basically. And as we saw on the previous slide, this is slow because the same match spec needs to be compiled all over again, and this happens like thousands of times per second. Now, as the Erlang efficiency guide says, an ETS table is a single key table and is to be used as one. In other words, use the key to look up things whenever possible, and that's what we do now. So we have a new table. It's called RabbitIndexRoot, and here we just split the destination queue in its own column. And we do the lookup by key now, so source exchange and routing key. And we use ETS lookup element, and that's much faster. So in this case, after this optimization, CPU time of RabbitExchange_root drops from 9.5% to 2.5%. And this speeds up end-to-end sending via the direct exchange type by 10 to 40%, depending on a number of factors, like how many publishers you have, how many bindings. This shipped in RabbitMQ 3.11. Maybe you might wonder, why did we store the binding as a key in the first place in RabbitRoot? The reason is that we also need to allow for high binding churn. Like, you don't need to necessarily optimize for high binding churn, but let's say you have clients which connect and disconnect often, and they declare queues and bindings very often. And in this case, we need to take care that we do not set a lock on the same record in the same amnesia table too often. So we don't want to have those lock conflicts and then amnesia restarts because transaction restarts, because that's very slow. So it often gets delayed by multiple milliseconds. Now here we could do the optimization for the direct exchange type. For example, other exchange type only use the source exchange to look up the destination queue, for example, the fan-out exchange, because the fan-out exchange doesn't care about the routing key. But again, here it's a bit too risky to include yet another index table, because if you have a lot of client connections which create bindings on the same source exchange, we risk that there might be many amnesia transactions, basically. So this is a second example of how CPU flame graphs helped. Here we have a process called ra_log_meta, which apparently is not able to process its incoming messages. So it has a backlog of 700,000 messages. This is the corresponding flame graph. I was giving a similar talk with my teammate Michal at RabbitMQ Summit, and he was saying this is the most obvious flame graph he ever saw. So it's quite clear what requires a lot of CPU time, so it's DETS lookup. And in this case, the change was dropping a single letter. So instead of DETS lookup, we now say ETS lookup. So they provide a similar interface, but DETS lookup does several discretes compared to ETS lookup. So in this case, it was simple because you already created ETS and DETS table for that process and synced the two. So whenever we insert into DETS, we also insert into ETS. And yeah, so the result with the same workload is that process now can keep up with the load. So no, not too much incoming messages in the mailbox. Yeah, that was it for CPU flame graphs. I didn't include any examples for memory flame graphs, but sometimes we also use mmap flame graphs. And yeah, one question?
Yeah, thank you for your presentation. So, difference with DETS and ETS is DETS writes to disk, right?
Yeah, exactly. So DETS is disk-based ETS basically, and similar interface, but the Erlang terms are just stored on disk. Yeah,
Right.
which is much slower. But if your node crashes, you still have the data after the restart. Yeah, exactly. And that's also what Amnesia uses underneath. So I think DETS got actually introduced just for Amnesia and was not originally designed for being used by Erlang applications, but that's what at least what I read in the book of Joe Armstrong. Yeah.
Okay, but you don't need it in disk. I mean, the reason why you could change it to ETS is because you don't need a copy to disk.
Yeah, exactly. So it depends on the use case. Like if you just want a cache, you just put it into ETS. It's much faster. Yeah, exactly.
Thank you.
Yeah, but sometimes you also use page fault flame graphs, for example, and then you see really in what function new physical memories being initialized. So yeah, I just recommend in your Erlang application, just do a sampling, create those flame graphs, and you see quite quickly what takes a lot of time. Sometimes it's easy to optimize, sometimes it's very difficult. I'm not sure whether the same works for Elixir. Probably as well, right? Has someone tried it for Elixir? Yeah. Okay. Then now we discuss a bit more general performance improvements across different queue types. So in RabbitMQ 3.10, Quorum Queues got optimized, so the state machine got a bit rewritten. And yeah, this is just one example. So in this case, we have 5 clients publishing to a separate Quorum queue, each at 5,000 messages per second. So in total, we end up with 25,000 messages per second. And here you see a Grafana dashboard after upgrading RabbitMQ from 3.9 to 3.10. And we just see that in 3.10, the line is much smoother. So this is messages published, meaning also confirmed back to the publisher. And in 3.9, it was very spiky, so it was between 20 and 30,000 messages per second. So that's not what we want, those huge spikes. Now this is Quorum Queues 3.9 versus 3.10 versus 3.11. So in this case, we have 2 publishers, 5 consumers, a single Quorum queue, and we send and receive at maximum throughput. Now the numbers you see here might be different on your machine. I think we did not use very big machines, so you might get even better numbers maybe. But yeah, in RabbitMQ 3.9, we achieve around 40,000 messages per second, so that's the blue line. Then in 3.10, the green line, that's where Quorum Queues got improved internally. We achieve around 50,000 messages per second. And then the interesting part is that in 3.11, it gets even a higher throughput. And that's although Quorum Queues did not really change much. There was some bug fix, but I haven't validated, or we haven't validated, but this is probably due to the routing optimization we saw early on. Because again, this perf command creates a direct exchange, a Quorum queue, and binds that Quorum queue to the direct exchange. Now, classic queues have been improved. So Loic worked on that for the last 1 or 2 years. So the persistent layer in classic queues has 2 components. the queue index and the message store. And there's one queue index per queue. And the message store is a key value store which is shared across multiple queues. So if you do, for example, a fan out, so you send a message to an exchange and then it ends up in multiple classic queues, this message is just stored once in that message stores. Now, since RabbitMQ 3.10, the broker also has a new implementation of classic queues named version 2. And that version 2 queues have a new index file format. And this is one result. So in this case, we can use perf test. We send and receive 100 messages per second. And every around 10 minutes, we increase the number of queues. So on the left, we have one queue. On the right, we end up with 25 queues. And as we can see, classic queues v2, which is the yellow line, has a much lower publisher confirm latency, so better. And on the right side, it performs also much better with many queues. So again, classic queues v1 are very spiky once you have many classic queues and they are under high memory pressure. This is the same workload, but this time with a message size of 5 kilobyte instead of the 12 bytes default message size by perf-test. And again, here we see classic queues v2, it's the yellow line. On the right, you see 25 queues, on the left, 1 queue. And we see that with classic queues v2, so the yellow line, we have more memory available, meaning they require less memory. So the main improvement of classic queues version 2 is improved stability while under high memory pressure. All right, so now we do a quick outlook on what we are currently working on. So we are trying to improve scalability for MQTT. We support MQTT via a plugin within RabbitMQ, so you need to enable that plugin. It ships with RabbitMQ. And how it works is that the MQTT plugin knows how to read the MQTT packets, and then it converts the message to an AMQP message and sends via AMQP 0.9.1, so it proxies via AMQP to RabbitMQ, to the internal Rabbit Erlang application. And that's actually a neat and nice mechanism to easily extend RabbitMQ with support for more protocols. So the same is done for AMQP 1.0 and for Stomp, for example. But what happens here under the hood is that the MQTT plugin, for example, creates an AMQP direct connection, it's called. So no real socket, for example, is opened. And that AMQP direct connection has, for example, a client in the MQTT plugin itself, and then also server side in the Rabbit Erlang application. And it also creates multiple channels for quality of service 0, quality of service 1, for example, so for MQTT at most once and MQTT at least once. It also creates, for example, an Erlang process or two actually, for the MQTT keep alive. So that mechanism got basically reused from something called Rabbit Heartbeat, because AMQP, in MQP is called heartbeating, and it's the same mechanism, just doing keep alive basically. But the point here is that for every incoming MQTT connection, RabbitMQ creates 22 Erlang processes. And while we know that creating Erlang processes is cheap, it does make a big difference whether you have 1 million MQTT client connections and 22 million Erlang processes, or just 1 million Erlang processes. So it makes a big difference memory-wise. So that's something I'm currently working on. We try to use native MQTT. So this means one Erlang process per incoming MQTT connection, and then we forward directly the message to the queue process. Now you might be wondering why we haven't done it this way directly. This is only possible because so Carl did some refactoring in recent years, so there's something called a new queue-type interface, and yeah, this makes the change much easier. Still a lot of work, but makes it much easier. And in this case, yeah, we achieve much better scalability and much less memory usage. Now, another thing we are working on, in particular Jean-Sébastien and Michael and Diana, is Capri. So Capri is a tree-like replicated on-disk database. It's based on the same Raft implementation Quorum Queues are based on. And it should become the new metadata store for RabbitMQ. So to store queues and exchanges, bindings, queues, permissions, and so on. And the goal here is to replace Amnesia within RabbitMQ. Now, why? Because it provides much better, like Raft provides much better network partition behavior than Amnesia, and also a bit faster transaction management. And one other advantage is, it's not listed here, but that maybe we can scale out a bit better. So with Amnesia, if you have those sync transactions, you're quite limited to maybe maximum 7, 9, maybe 11 node Erlang cluster. So this should get a bit larger with Capri. So we won't end up with, I don't know, 100 nodes, but maybe a few nodes more at least. Then something we have experimented with, but currently we're not actually working on that actively, is continuous profiling. So we wrote Kubernetes operators, for example, to easily deploy RabbitMQ on Kubernetes. So for example, we have one operator which is called the RabbitMQ cluster operator. It knows how to deploy RabbitMQ clusters and how to manage them. So with just a few lines of YAML codes, you can spin up easily RabbitMQ clusters and update them, which is cool. We have another operator, by the way. It's not related to this topic directly, but just to mention it, we have another operator. It's called the messaging topology operator. With that, you can declaratively declare queues exchanges, for example, so your client applications don't have to do it. Anyways, so we deployed RabbitMQ on Kubernetes, then we installed Parker. So Parker is a tool which allows to create those CPU profiles for multiple nodes, so for the entire RabbitMQ cluster, and for doing so in production. Earlier on the example we saw, this was just doing a one-off profiling in development node of a single node. Like with Parker, we get those nice flame graphs for an entire RabbitMQ cluster. And they also have options to diff different profiles. So for example, we can compare different versions of RabbitMQ with the same client workload, or diff the same RabbitMQ version but with different client workloads. So this is more or less how it looks like. It's just basically inverted, so they call it icicle graphs. But the problem is here that today some Erlang debug symbols are missing in Parker. So if someone of you has maybe tried it out and knows how to do it better, let us know. But that's something we might want to work on also in the future. Like in this picture, you see the function names resolved, but actually most of the time they're not getting resolved. So again, this is Parker, and the problem is probably in Parker somewhere, but we haven't investigated too much. That's it for the talk. Thank you for listening.
Right. Okay, so I guess we have some time for Q&A. I don't know if there are any questions virtually. I don't think so. There are, right? So in person, anyone has a question for David? Right. So no questions then. Okay. Then thanks, David, for your talk.
Thank you.